That was very sudden and abrupt. Hey, what's up, skeptics? Welcome to another episode of Reason to Doubt, your source for all things skeptical. I'm Jordan, and Jared is with me, back again, recovered from COVID.
Almost 100% now. I'm feeling much better. So
awesome. Glad to hear it. So today we are going to be talking about young Earth creationists and why their model would cause Noah to burst into flames before I'm not sure what would get him first, if his blood would boil, if he'd just be incinerated. I don't know. But there'd be problems. The Earth would be a giant ball of radioactive death. And so it wouldn't be a good time.
Before we do that, though, before we talk about balls and death, let's talk about fallacies, because we do that here.
Fallacy of the day is one I've been seeing running around Twitter kind of in the wild recently. It's the base rate fallacy. So this is a fun one. It has to do with statistics, and who doesn't love statistics? Everybody. So this fallacy happens when you fail to take into account the general prevalence of a thing when you're talking about the likelihood of a thing. This happens all of the time in medicine and when science reporting in general. So one example of this, I saw recently the statistic: about half of people who die in car crashes are wearing seatbelts. It's like 51%.
That proves it then, right? Seatbelts don't save lives.
They don't do anything. I mean, if you're wearing a seatbelt, 50-50 shot that you're going to live. So who needs them, right? Of course, that doesn't take into account the fact that over 90% of people driving wear seatbelts. And so if seatbelts had no effect, you'd expect the number of people dying while wearing a seatbelt, like of the people who die, how many were wearing seatbelts would be
90%.
90%.
Yeah, okay, I got it.
Very good.
Statistics.
So the fact that though non-seatbelt wearing people only take up 10% of the population, but are 50% of the deaths, that shows that they're disproportionately represented in the sample of people who die not wearing a seatbelt. So you have to take into account the overall population when you're looking at statistics. The way it often is used is things like for COVID, for example. Well, the majority of people who get sick or die were vaccinated. Well, but if 80% of people are vaccinated,
and only 10% of vaccinated people get sick, then something's working here, right? I don't know if that's a right number or not, but
right. So that's the base. Yeah, that's the base rate fallacy. Just it's an easy pitfall to fall into. So that's why there are people who are paid to do statistics. It's not easy.
So tonight's topic, you're talking about the heat problem, and you've mentioned young Earth creationists. In case somebody doesn't know or familiar with young Earth creationists, what exactly is a young Earth creationist?
Great question. So a young Earth creationist is a term broadly for someone who believes that the Earth is young. And by young, they usually mean somewhere in the neighborhood of 6,000 to 10,000 years. And it usually applies to people in an Abrahamic religion. So in America, they're typically Christian, but you get similar claims from some sects of Judaism and Islam as well, but Abrahamic religions usually.
Okay.
And they believe it on the basis of Genesis.
And so I imagine that the problem then comes from the truncated time frame that we're working with here. Is that?
Well, so there's a lot of problems with young Earth creationism, and I used to be a young Earth creationist.
So you can talk about them then,
right? Yeah. So I like to think that gives me a little bit of special empathy for this group, but so yeah, there are a ton of problems with young Earth creationism. Basically, pick a field of science, and there are problems. But today, the problems we're going to be talking about have to do with thermodynamics and also with radioactive decay. So that's kind of the problem here. And like you said, it has to do with the truncated timeline. Heat, the rate at which you release heat is important. That's why if I touch this cup, it's fine. But if I touch a hot metal pan, it's not fine.
Right. And from the outset, this is not my area of expertise, and I'm a layman on this subject. So my role tonight is actually just to make sure that Jordan doesn't go into the land of gets so technical that people like myself can't understand it. So I might have to say, hey, let's reel that back in and explain that Barney style, please. Like, yeah.
Hey, Luca. Nice to see you. Make sure Luca is another professional scientist who's going to keep me honest on thermodynamics. Make sure I don't mess up. Paleologos has a good point. Almost everyone who's ever died wasn't subscribed to him. So therefore, yeah, I mean, I'm not going to tell you that subscribing to Paleologos will save your life, but it probably won't hurt, right? So why not? Okay. So heat problem. Before I get into the actual problem, I think it might be helpful to back up and talk a little bit about radioactive decay, just in case, I don't know, somebody in the audience isn't intimately familiar with how radioactive decay works, just in the off chance, you know. So in the universe, there are atoms that are unstable, not happy with their lot in life. You've got in their nucleus, which is the center bit, the thing that makes it an atom, there's protons, and if you're more than hydrogen, neutrons. And protons are positively charged and neutrons are neutral, right? And so as you know, if you ever tried to like mash a magnet together, positive things like charged things don't want to touch, right? And so there's that electromagnetic force trying to force the protons away. The thing counteracting that is the strong nuclear force. That the specifics doesn't matter. Basically, you can imagine that the neutrons are kind of like playing referee and giving the protons enough space to breathe so they don't blow apart. That's not physically what's happening, but that's good enough for conception, right? And so as you go up the periodic table and get more and more protons, you need more neutrons to keep it stable. And eventually, either you'll have too many or too few neutrons, and you'll be unstable. Or once you get past a certain point, you just can't be stable. There's no stable configuration. And so when you're unstable, you being this atom, you want to get to stability, and you do that by decaying in some way. You kick out some kind of particle and heat and become something new. And that process continues until the thing you turn into is stable.
I understood all that. So we're
great.
Good.
Okay, cool. Yeah. With me so far. All right. So the key things there to keep in mind are that when something decays, what radioactivity is the process of decay. Okay. And the rate of the activity of a sample is how many times it's decaying per second. The units are becquerels. Units don't matter. It's just how many things are destroying themselves each second. And that's where the half-life comes from. You've probably heard of that. Like the half-life is how long it would take for half the sample to go away. If you have a kilogram of uranium and then you wait a half-life, which you're going to be waiting a while because it's billions of years, you'll have half the kilogram at the end. That's all related.
Yeah. Okay. Most people have heard Half-Life. It was a great game in the 90s,
It was. Yeah. Well, so I heard. I actually have never played Half-Life. I kind of missed that one, and I feel like it's too late now. Anyway, so how does this tie into young Earth creationism? Well, there are things that we can observe in reality that appear to have required a lot of radioactive decay to get to the point where they are today. There's a lot of things that are like this. You've got some radiometric dating results where like you date a fossil where the rock's around a fossil and it says it's so many billions of years, or and other things. One thing that my favorite thing to point to is the naturally occurring nuclear reactor at Oklo. That's my favorite thing because one, it's the coolest thing to have ever happened ever. And two, because most creationists also agree that's what happened. So in brief, in Oklo in Africa, there's a uranium mine and they were mining uranium, and it's very important to know how enriched the uranium. Enriched in this case means you've got two different kinds of uranium, the good kind, the fissile kind, and the non-fissile kind. U-235 is the good kind. However much of that you have in the uranium, that's how enriched it is. And in nature, it's about 0.7%. When they dug it up at Oklo, it was less than that. By like 0.6, 0.5% may not seem like a big deal, but that's a big deal because uranium goes missing, people notice, right? Yeah. And so there was some concern that like something had gone wrong. And when they investigated it, it turned out that no, the uranium from the ground was actually depleted. And when they investigated it further, it appeared that what had happened in the past was a natural nuclear reactor had depleted the uranium. So here's I'm going to show a picture to explain this because I'll take literally any opportunity to talk about Oklo. So let me share my screen there. So nuclear reactors require a few things to work. You need uranium or some other fissile thing. We're talking uranium. It needs to be enriched to about 3%, which means 3% of the uranium is that U-235. Then you need some kind of thing to slow the neutrons down. In this case, we're going to use water. And if you put those things together, you get fission because the neutrons are bouncing around in the water. They get slowed down. They get sucked into a uranium atom, which then fissions and makes more fission. That's how that works. Okay. So uranium over time is getting less enriched because the fissile stuff decays faster than the non-fissile stuff. So over time, you're getting less of it. The curve looks like this. So you can see your enrichment over time is going down. All right. Wind that
And
back.
so fissile just means something that's able to have fission. Okay.
Yes, exactly.
Yeah.
Yeah. That's what I mean. I'm trying to cut down the things that you need to know and not like go running off into other things. Okay. So yes, fissile is the stuff that's doing the fission. Okay. And so if you go backwards in time, assuming current rates, which I'll get to that in a second, you get to a point where the uranium would be 3% enriched. And so would have sufficient enrichment to cause fission. And that appears to be what happened at Oklo. And the way we know that is because not just the depleted uranium, but there were also fission products that only occur in nuclear reactors in the proportions that they were there. Okay. So it's very good evidence that there was a nuclear reactor there. Okay. I struggle to imagine another way that could have happened.
I mean, somebody buried some uranium there that had already been in a reactor or something.
Yeah, something like that.
Yeah.
Okay. So we've got this phenomena, and it requires 2 billion years worth of decay to get to where we see it now. Okay. So this is where we're going to tie it back into young Earth creationism. You've got 2 billion years worth of decay, but only 6,000 years for it to have happened in. Right. So that's a problem.
It's a big problem if there's only been here for 6,000 years, right?
Right. You can't have this uranium, which is older than the universe.
Yeah.
So one of the ways in which not just this phenomena, but the phenomena of requiring more decay than you could get in 6,000 years, one of the ways that that's addressed by creationists is they say, well, maybe things decayed faster in the past. Like right now, they decay at this certain rate and we can measure it and everything's great. But you weren't there so many thousand years. What if it was faster? And then you could get all this decay to happen in that short time frame. And yeah, no problem. Boom, problem solved. Right? Wrong.
Well, that may solve the problem for the timeline, but it creates another problem, right?
Right. It definitely causes some other problems because you can't just do that in a vacuum. You can't just increase. So remember how I was talking about how like radioactivity is like releasing heat and radiation? If you decrease the half-life, you increase the radioactivity by definition. How radioactive something is that's the definition of the half-life. They are the same thing. They're just two different ways of looking at exactly the same thing. Mm-hmm. So if you make it decay faster, if you make it so you reduce its half-life, it's going to decay faster. You're going to have more disintegrations per second, right? Which means you're releasing more heat and more radiation. So they've got 2 billion years worth of heat and radiation that they need to cram into 6,000 years. And that causes problems. So if everyone's caught up, this is where the math comes in, but I promise I'm going to keep it light and it's not going to be very confusing. Okay, so if there's no questions in class, now we get to the fun part. We're going to melt the Earth now. Okay. So I show my other screen. We're going to talk about how much decay we would need. Okay. So this is the formula for radioactive decay. This just says how many things you have now is equal to how many things you used to have times this stuff, which is how fast it decays and how long it's been decaying. That's all it is. Okay. This is how the decay would look like if you put it on a curve. These are how many atoms have decayed in 2 billion years' time using the current rates, but it doesn't matter because that's the number of atoms, whether they did it in 6,000 years or 2 billion years, whatever. That's the number of atoms that you would need to have decayed, right? And so what you do is you figure out how many atoms are going to decay. Okay, how many of the relevant atoms, uranium, thorium, potassium-40 in the crust. You determine how much there is right now. You determine, then you can back calculate to how much would have decayed. And then you can calculate the energy for that decay. Okay, so it's pretty simple. Here's a bunch of stuff about the Earth and the prevalence of things. And I'm going to, if you look in the video description, calculations and stuff are in a Google Doc, which are way easier to read. So if you want to check my work, you want to whatever, just go down there and you can follow along. It'll be a lot easier for you. Because that's there, I'm not going to pause a bunch and read all this to you. But there's stuff about uranium. What it comes down to is this is how many atoms you'd need to decay. But there's more, because if you decay uranium, right, it doesn't just like stop there, because not only is the uranium not happy with its life, the thing it decays to is also not happy with its life, and that thing is also not happy, and it just keeps decaying. And every step along the way, until it gets to lead, which is stable, decays and has half-life and releases radiation and heat. So once I figured all this out, then I had to go to the chart of the nuclides and go through the entire decay chain, which this is the decay chain for the 3 different isotopes. You can see how it bounces around the whole way, and there's different pathways because it has a probabilistic distribution of going one pathway to the other. So you have to like weight it and do a bunch of fancy math, which again, on the Google Doc, go check that out. So I summed all of that up. I did all that work, okay, to figure out like how many atoms would decayed, all of their daughters, all the way down to lead. This is an example of what that looks like. And what that left with was this, the final answer of how much heat would be released in the crust. More is happening down in like the mantle, but this is like the crust itself. I was able to provide these calculations to Luca, who was able to use it to great effect in his discussion with McQueen. McQueen is one of the resident experts on this problem. He's a really nice guy. McQueen is a really fun guy to talk to. I'm not sure he has a lot of expertise on this particular problem, but he's a good guy nonetheless. Anyways, so I did these calculations, and you get 0.5 times 10 to the 30th joules that are being released. And as like a check on myself, I used some measurements that were taken using neutrino emissions from below. So like when one of the things being released by these decays are these particles that don't interact with matter very much, called neutrinos. And by seeing how many neutrinos there are, they can like determine how much decay is happening. The people at Camland did that, and I checked my calculations against theirs, and I got within 6%, which I think is pretty darn good for some like Excel back of the envelope stuff I was doing. I'm pretty happy with it.
What's a joule?
A joule is a unit of energy.
Cool.
You've heard of a watt? Like,
yes.
You've got a watt is joules per second.
Got you.
Right. So if you were releasing all of this in a second, you'd have 0.5 times 10 to the 30th watts.
Cool.
Yeah. So there you go. So that's how much energy is released. And that number probably doesn't mean a whole lot, right? It's a big number. There's like a exponential there, but like, what does it mean? You know,
it's like telling me how many millimeters are in an inch. I don't know. It's like,
yeah, you don't know. Who cares? What's the big deal?
Yeah.
So if you imagine physically what's happening, right? You've got most of the crust is actually enriched, meaning it has more radioactive material as opposed to the rest of the Earth.
Mm-hmm.
So like about a third of the uranium, thorium stuff is in the crust, right? That very thin layer. And so the heat is released there. Heat always flows from hot to cold, right? Never the other way around. You don't open your air conditioned. If it's a hot summer day and you open your door, your house is not going to get colder. It's going to get hotter, right?
Have you ever seen the movie Backdraft? You know what happens when you open the door. It's like,
right. So the mantle is hotter than the crust. They darn well better be, because it's like molten down there. You know, if we're allowing the crust to heat up to the point where it's like the temperature of the mantle, you've got big problems already, right? And so that heat is there's only one other way for it to go, and that's up through the crust, through the water, the flood, and now we're back into Noah. Okay, so the reason I mentioned Noah is because maybe I can explain the units of measurement better. Well, newtons is a measurement of force. So like if I'm pushing something, that's force, right? Joules is a measure of energy, which is, for all intents and purposes, here heat. You can do a calculation to convert your joules to calories if you wanted to make it more palatable, I guess. It doesn't really matter like what precisely a joule is. I'm going to give you like more concrete terms to fasten to it. It's just a unit of energy. So back to the creationist model. So they know that they need to have this crazy thing happen. They need all of this decay to happen in a very short period of time. So what they will often do is say, well, it happened during the flood, Noah's flood, which covered the world in water and was a big catastrophe. That's when all of this crazy physics stuff was happening.
And since we use water to cool nuclear reactors and stuff, bingo bango, right?
Right. And you've got all this radioactive stuff down below, but you've got all that water between him and Noah. No problem. Problem solved, right? Well, you did have 6,000 years to do this. Now you've got like a year, right? So now we're cramming 2 billion years worth of decay into 1 year. So what does that look like? Well, it's going to start in the granite, right? So you can do a calculation to see what the temperature increase would be in granite. It is the name of the formula. It's a specific heat calculation. And I'm seeing if I have it on my presentation so I can show someone. I don't. It's in the Google Doc. So you basically use the material. It has a property of like how many degrees Celsius it would go up for every joule it accepts, right? Now, this is assuming you don't go through a phase change or whatever, but if you run that calculation and you said, okay, it's going to take all of this heat, what would happen? Your granitic crust of the Earth would be 27,000 degrees Celsius, but you could just say Kelvin because at that point it doesn't matter. They're basically the same thing. For scale, the surface of the sun, let me just look this up real quick. The surface of the sun is 5,600 degrees Celsius.
Okay. Last time I checked, there wasn't any water on the sun.
No, don't think there is. And so obviously the granite would not actually get to 27,000 degrees. It would vaporize long before that, right?
Right.
So, but if you're to the point where you're vaporizing the crust, you've got problems, right? Okay. But what about all that water, right? You got all that water. Well, water also has, only so much heat that it can take, right? That amount of heat, even if you take all of the water that would like cover the Earth, like all the water that is on the Earth plus some extra, multiply that by 10, like give them just an order of magnitude, and you're less than 1% of the total energy to boil the oceans. Like all of the water that Noah's boat is in is vapor and superheated steam. And we're still like still got 99% of the heat to go, right? So it's a problem. It would like melt the Earth. Other mechanisms they use to try to explain this are things like hypercanes. Like, what if you had like these huge hurricanes that were like drawing heat up?
Cooling fans that are like shooting heat out of the atmosphere, right?
There's all kinds of problems with that. First of all, where's the heat going? It's going into the atmosphere still. Like, it doesn't like have a fucking magic portal to space,
Yeah.
Like that's not how that works. But even if it did have a magic portal to space, I did the calculations for that too. And if you had hypercanes, and so they call hurricanes in their parlance, hypercanes are like super mega hurricanes, right? And so even if you said the hypercanes are 10 times as powerful as hurricanes, and they covered the entire Earth, 100% of the Earth's surface is hypercanes, and these hypercanes are going for the entirety of Noah's flood all year. It's a wall-to-wall, 365, 24/7 hypercane bonanza. That amount of heat, I'm going to show you because it's very simple. You can just plug. This is how it looks like. You've got the water vapors collecting, it's condensing, which there's a latent heat of condensation that gets released to the atmosphere in reality. But let's say it beams to space, right? And then you've got that water cycle. This is how that would work. The amount of heat times the amount of waterfall that's going down over the area times the latent heat of condensation times the time of you're doing this, okay? And you just plug in all of those numbers and you get 0.02% of the total heat you need to release. And that's for covering the entire world in hypercanes for a year. right?
That
Like
does
this,
that doesn't. That's like putting a band-aid on a. That's not even putting a band-aid on. That's like,
not even.
yeah.
That's like thinking you might have a Band-Aid one day. It's
It's
like,
like I know about band-aids. Yeah.
yeah, you could have 100 different methods equally as powerful as these absurdly powerful hypercanes, and you still wouldn't scratch the surface of the amount of heat you need to release. So yeah, it's just not enough. But it gets even worse, right? Because that it's not just things that are happening below the water. People, you like to think of like radiation as something that happens far away, but you are radioactive. So am I. So is everybody. We all have radioactive isotopes in our body. Carbon 14 is one that people are probably familiar with, but potassium 40 is in your blood right now. A portion of all potassium is radioactive, and you have potassium in your body. So a portion of that potassium is also radioactive. And I don't care how much water there is, there's no amount of water outside the boat that's going to protect Noah from the potassium in his bloodstream, right?
Yeah, true. True.
And that potassium, if you do 2 billion years worth of decay, is enough to boil him alive from the inside out. Like the instant this gets kicked on, he falls over dead because he's like cooking from the inside out. But wait,
Oh, man.
there's more. Like it gets even worse because all we've been talking about is heat, right? Like all this time, the only thing we've been talking about for this radiation is heat, but radiation also releases radiation, like the scary stuff that people are afraid of with nuclear plants for,
Yeah, the
right?
stuff you see in movies where they can put the suits on and
Exactly, right? It's also releasing that. So if you do calculation, and this one's pretty easy because you can just like, how much radiation do you get from your food each year? You can go to the NRC and they have calculations for that. And just do 2 billion years worth, because that's how much you're getting, right? It's just the 2 billion years. It's not a linear scale per se, precisely. You'll be a
right.
little bit off, but it's close.
It's a rough estimate.
You can get kind of order of magnitude if you do that. The amount of so the unit I'm going to use here is millisieverts. Again, don't worry about the unit, just for some scale. Like a radiation worker, the limitation for their dose is 50 millisieverts for a year. That's your scale. Okay. The lethal dose is about 8,000. Noah's dose that he would be taking every single hour from his food and water is 78 grand. Like almost 10 times a lethal dose straight to the organs every hour.
Oh, man. Yeah.
Yeah. So yeah, Luca's correct here. More like he'll explode in a spectacular fashion while the boiling water. That's a good point because he wouldn't just like fall over dead. All that boiled water now has pressure on the inside, and he's gonna be like, the body is not a very good pressure cooker.
No.
Yeah,
Oh,
that
man.
would not be pleasant.
So is this an example of somebody just trying to come up with an ad hoc explanation for something and then without thinking the ramifications?
Yeah, so this is an example of coming up with an explanation for the problem right in front of you
Mhm.
and not applying the broader implications. Now, to some creationist credit, like the more professional organizations, I'm thinking like Answers in Genesis, or well, not Answers in Genesis, really, ICR, like the Snelling, Andrew Snelling, who's one of the big names in creationist field. He's done some calculations on this, and to their credit, they acknowledge that the heat problem is not something they have an answer to, and many of them will say it may require a miracle, which fair enough. Like God's
You
all
already have a
powerful,
miracle because it's raining, waters are coming from somewhere, right?
right?
Like,
Fountains of
yeah.
deep and all that stuff. Like
Yeah.
fair enough. Like you're talking about a very supernaturally charged world. God intervened. Okay. But I think the problem comes with the drive to want to avoid invoking that, because it's almost like a cop out, because
Right.
if God can just use magic, for lack of a better term, at any,
Yes.
then why bother examining any of this, right? It should just all be magic,
Yeah.
But then where does that stop?
Seems like in my experience, young Earth creationists really try to hit that they are being scientific, that they're using science almost as a form of credibility, but also to try to maybe persuade some of the more scientifically literate people to come into their side too.
And I mean, I think for at least some portion of the the creationists, they honestly want to know the world. They want to like answer these questions, and science is a way to do that, right? That was my attitude as a young Earth creationist. But the problem is that there's some tension there. The scientific method doesn't allow for miracles, because if you can just invoke a miracle whenever you want to answer your question, well, like what are you doing? Just say it was a miracle and go home.
Yeah.
So that on the one hand, there's a tension where they want to avoid invoking miracles, but you get painted into these corners, um, but because you're constrained to it can only be 6,000 years. Well, that has implications. That something's got to give at some point. Something's got to give. You know. So, but you also, on the other hand, another explanation is, well, God created the isotopes and their current prevalences in the Earth as they are
The
now.
appearance of age or something like that, right?
Exactly.
Yeah.
And the line usually goes something like, well, Adam, like when he was created as a fully grown man. And like if you were to look at him, he'd appear to be, I don't know, 30, however many years old. But he would have, in fact, only been a couple days old, right? So the Earth, maybe it's like that. But I think if you do that, you've run into a situation where God is deceptive, because he created it. He wouldn't. There's nothing forcing God to make all of the uranium across all the world to have 0.7% enrichment. Like,
Right.
There's you could easily if you're God, you could make it all over the place, right? But if he made things the way they are, then he made it such that someone looking at the rocks and just doing the math with the physics, just without knowing what he did, would come to a wrong conclusion and have no way of telling, right? It seems not that far off from like last Tuesdayism. He could have
Yeah.
created the Earth last Tuesday with all of the
All the
memories we have
memories
now.
are in our brain. Yeah, exactly. Yeah.
Exactly. There'd be no way to tell different. But like, why do that? Like, I don't find solipsism personally very attractive. So,
Yeah.
and if God is supposed to be good, God is supposed to be, loving. It doesn't seem very good or loving to effectively lie to his
Yeah.
creations, right?
Deception seems outside of the character of most descriptions of God. So,
Right.
yeah. Although, I mean, last
Well,
Tuesday. So,
yeah. So I think you kind of you're stuck between, on the one hand, you want to use science, you want to avoid invoking magic, you want to like actually learn about the world, but on the other hand, you've got these very rigid, like this rigid conception of what the truth has to be. You've started with your conclusion, you're working backwards from there, but there's a disconnect. Now, I struggled with this myself when I was deconverting, and I eventually just had to decide to set aside those constraints. Like,
mhm.
I'm just going to ignore what I think I know, what the conclusion I already believe, that the Earth is 6,000 years old. I'm just going to put that aside, and I'm just going to look at the evidence. And if the Earth is in fact only 6,000 years old, the evidence will tell me, right? Like
It
it
should.
it should, right? The truth shall set me free. So if I just look at the evidence and follow it wherever it leads, it will lead me to the truth. And if I'm right, then it'll lead me right back to where I was. But if I'm wrong, I want to know. And I
So I
think,
guess, yeah. I want to know if I'm wrong too, but obviously this stuff, the math is way beyond my skills, my abilities, and I imagine it's beyond the skills and abilities for most people, right? But
yeah.
when presented to it in the manner that what you did, I can see like, yes, this is definitely a problem, and I'm not going to go and learn all the skills needed to come up with that conclusion, but I can stuff. If I was a young Earth creationist presented this, how do I still maintain that belief? Do I just have to keep coming up with explanations, or I don't?
Um,
That's what boggles my mind.
So I don't want to speak to a community that I'm no longer a part of. I can say that often now I think it's fair when presented with this, you don't necessarily immediately change your mind, right?
Yeah,
You have to take some
there's a
time and investigate it.
process.
I mean,
Yeah.
I'm just some random engineer on the internet. What do I know? But uh, often what I see is they're just constantly looking for that next thing. George Bond and McQueen, who we mentioned earlier, I presented these things to them. They don't have an answer. And they like come up with vague explanations like, well, there's these blobs under the mantle that are like hotter than the rest of the mantle. So maybe the heat went there, ignoring that undermines the second law of thermodynamics, because heat goes from hot to cold, not cold to hot, right?
Right.
So you can't use the mantle as your heat sink because it's hotter than the thing you want to cool down. Uh, yeah. So honestly, the way that they answer it, you can go the professional route, which is just to say exotic physics or supernatural causation. We don't know, which fair enough. Or you can go the George Bond route and just say, we have an answer and we have calculations. They're super awesome. We're not going to tell you. We don't have the calculations, but I promise they're great. You can go that route, I guess.
Lot of people are saying they're the best calculations ever.
Yeah, the best. Just huge
Huge.
calculations. Yeah, so those are the routes I think that are open to you. And it's a fair point, like you brought up. The calculations I did, while they're not super complicated, I wouldn't expect somebody who's like never studied nuclear anything to like know to get from A to B. Like how would you know like what math to use, to do the big league calculations like they said. Luca hit the nail on the head. The SFT brain trust is to keep things long and complex and no one to follow. If you've ever seen SFT's channel, there's like their streams are like, no joke, some of them are like 5 hours long. I don't know how they have the stamina for that, to be honest. Yeah. Anyways, so yeah, I wouldn't expect some random person off the street to like know how to do these kind of calculations. That's totally fair. That's why we specialize, right? That's why we have a scientific community. That's why we've got people who spend all day thinking about these kind of things. And it seems implausible that every single one of them is like in on the conspiracy. I'd have to be in on the conspiracy, right? Like I'd have to.
Are you?
I mean, I'm not gonna. If I were, I wouldn't say I was, right? Because then they'd stop paying me. Yeah.
Well.
So that's the heat problem. That is just one of many, many problems with young Earth creationism. I think this alone should, in my humble opinion, should be enough to persuade someone to abandon the idea that the Earth is 6,000 years old. It's just so much simpler to just, the Earth is old. It's not a big deal. And like, that's the stance of the vast majority of Christians.
Right. You don't have to give up your faith at that point. Like you can just.
No. Most Christians you run into, even in America now, but certainly globally, don't think the Earth was 6,000 years old, and they still go to church and take communion and pray and do all the other good Christian things you should do. Like, it's not a big deal,
Right. The only thing it really affects as far as your faith is the understanding of like inerrancy or like a literal interpretation of the Bible, right? So like you'd have to make a big adjustment in like how you view scriptures and the Old Testament, but at the same time, it doesn't really affect much of the practical side of Christianity.
So for me, when I was a young Earth creationist, I had been brought up to believe that if the Bible was not literally true, then faith was dead. And I think that that's a big problem. It's not a good strategy, because you're pitting like your very specific interpretation of this book against, and you're betting all in on that one interpretation. And if it's wrong, you've told everyone, if it's wrong, you should not be a Christian. I'm not saying every young Earth creationist believes that. That's what I was told, though. And bro, it's not that's not a winning strategy,
So this is more of a personal question, but when you, on your deconversion or your, whatever you want to call it, did you ever flirt with old Earth creationism, or did you go straight to?
Yeah, I kind of like ran the whole like rainbow gamut of Christianity on my departure from it. So I started like young Earth creationist. I was like, oh man, the Earth isn't young, turns out. Okay, I guess it's old. Like maybe I'm an old Earth creationist. I was like, oh, well, maybe God doesn't seem necessary for that. Okay, maybe I'm theistic evolutionist. Oh man, doesn't seem like he's necessary for that either. Okay, we'll back up further. Like
the domino started falling. Yeah,
that was my process. But I'm only one person. Not everybody has to take that process. That there are people that I respect greatly who believe that God is. They're Christians, and that they don't think the Earth was 6,000 years old. So I don't think those two things are necessary. And also, I think you miss some of the poetry of the Bible by interpreting it in this rigid way, right? Like, you've studied the Bible way more than I have, but if we allow it to speak to us the way it was written, like let the voice of the authors speak to us, I think you get a much more beautiful story. So I saw a great explanation of like the Genesis story, like why a flood, why was it like that, right? Why drown the earth? And the explanation I got, which made a lot of sense, was the original Hebrew cosmology was you had the flat Earth, and you had the firmament, which were water, like literal water above and below in space, and when God is looking over he's looking over the chaotic waters originally, and he like literally parts them to make the Earth dry. Like he's like pulling them,
little air bubble right in the middle. Yeah,
bubble, exactly right. He parts the firmament above and the firmament below, right? And so that's the Earth he created. And then later, when he was saddened because people were like sinning and like his creation was going to shit, he is like, you know what? I'm going to return things to the way they were. And so waters came up from above and below because he's returning it to the chaos it was before. That's why it's a flood, because it's restoring the creation to its original form, because he's kind of like wiping it away. And that's a much more poetic, like beautiful. Well, I still think it's a effing horrible thing for him to do, but at least it like makes sense, you know. Like there's like there's some poetry there, I think.
Yeah. Especially if you're taking it from a non-literal like.
Right.
But yeah, I agree with you there. So.
Yeah. So I think we've said all we need to say. In summary, if creationists were correct, young Earth creationists who take to this particular model, I should say there's more than one model of young Earth creationism. They all have their own flavors of wrong. So these particular calculations apply mainly to catastrophic plate tectonics and the people who want to cram radiation, 2 billion or really 4 billion years of radiation into a year. Other models have different problems. But if the people who subscribe to this model, which is pretty popular, were right, then Noah would explode like a popcorn. Yeah. Probably
pretty fast too.
Very fast. Probably not as tasty though. Yeah. So do all the YouTube things, like, comment, subscribe, you know, all that sort of stuff. If you thought it was cool, if you didn't think it was cool, let us know what you think, if we missed something, and tell us if there's something you want us to tackle in the future. We're always looking for new videos, anything to do with any claim. Doesn't have to be religious, whatever. We'll do whatever you want. We're here for you. For the low price of absolutely nothing. Just hit that like button. Yeah. So you got anything else?
Nope, that's it.
Cool. Well, thanks for joining, guys. And remember, till next time, you've always got reason to doubt.
Peace out.
Oh,
wait, there's more.
Sorry, one thing. I forgot. We're upcoming. We're talking to an atheist who lives in Africa. And he has a very similar experience to us. So we think that's going to be really cool. I think we're going to be doing that. Should be posted next week. So look out for that.
Yeah.
Some cross-cultural contamination there. Anyway, you've always got reason to doubt.
Peace out.